Hi there. Thanks for getting to this video lecture. As promised, we will wrap up chapter 16, and I thank Mr. Kyle again for helping with lecture 7, which was a continuation of what we started in lecture 6 with Coulomb's law, electric charges, and now electric field. Mr. Kyle already started electric field here, which basically helps us visualize how charges exert forces at a distance, and he solved some problems for you. The aim of this lecture is to review what he did, the slides I gave him to go through with you, as well as take you through very elementary aspects of Gauss's law, as we have agreed in this lecture. I mean, when I say we, all the other instructors. So the much that we've agreed to do in terms of Gauss's law, that's what we will cover, and you'll be good enough to do the homework that is due on Sunday night. All right, so electric field, even in cell membranes, we have very strong electric fields thanks to ions, charges, so charge carriers in ionic form that exist outside and inside the cell. So in the cytosol and outside the cell, there is charge separation leading to an electric field across. All right, where are we? The key thing to note is once more March 1st, we have exam 2. And I hope that we are getting ready for it, our usual strategies. All right. Once again, I'm very happy with your performance in exam 1. Mr. Kyle may have shown you this slide, but let me reiterate that many of you did very well, so please keep it up. And those who need to improve, please try to do so. Now, the concept of the electric field continued from lecture 7. What does it do? What is a field? Well, a field in physics is a region under the influence of some physical force. If the force is gravitational, then we've got a gravitational field. If the force is magnetic, then we've got a magnetic field. And if the force is electric, then we've got an electric field. In fact, we can calculate the force, the electric force in this case, if we know the electric field. As you can see my pointer. So the electric force is given as the product of the charge that you have and the electric field in which the charge is under the influence of. So if a particle with charge Q is placed at a position where the electric field due to other charges is E, then the force on this charge Q due to the electric field created by other charges is given by this formula, and you have chance to work on this in flip it problems. All right, so once again, please try to do in detail the 3 problems I gave earlier. And what are those problems? Here you have a question on the strength and direction of the electric field at the point, this point. So you are asked to specify the direction as an angle above or below the horizontal. So some hint here is that you try to find the x component, the horizontal component of the electric field, which will be due to the positive charge as well as the negative charge. And you also find the vertical or y component of the electric field. In this case, the y component of the electric field due to the positive charge will be 0. So you are only left with the y component of the electric field due to the negative charge. And after that, you do a vector addition, okay, which is reminiscent of what you did in Physics 201. I can help more during the help session on Friday. I'll be there. So the second problem is still the same strategy. First of all, at point A, find the total x component of the electric field, which would be x component due to 5 nanocoulomb charge and x component due to negative 10 nanocoulomb charge, x component due to 10 nanocoulomb charge. Incidentally, the x component due to the 5 nanocoulomb charge is 0. And the y component due to the 10 nanocoulomb charge is 0. So when adding the total x components, you will have x components due to negative 10 nanocoulomb and 10 nanocoulomb, but you will not have an x component due to 5 nanocoulomb. I hope the point is clear. All right, this is another very interesting problem, very much like the flip it as well. Here you are asked to find an electric field, or you are given an electric field. See it here, 200,000 newtons per coulomb. The electric field is to the right, and you are asked to find the angle. Since the charge is at equilibrium, this charge, the total force on the charge is 0. But what are the forces on the charge? This is the key to understanding this problem. The forces on the charge are 3. There is tension from the string. There is gravity, gravitational force down. And of course, there is the electric force. So if you do the 3 forces, you can resolve and then obtain the angle. A little bit more on the electric field concept. In very simple terms, if I have a positive charge, such as this little q here, and I need to know the direction of the electric field due to the bigger charge configuration, big Q, then what I do is to bring this test charge, usually positive, and the direction in which I feel a force on the little q charge due to the large q charge, that is the direction of the electric field. So think of the little q as being positive. That's why we have q greater than 0. Now I place this charge here because big Q is also positive. Positive and positive repel. So the little q charge is going to feel a repulsive force in this direction, and that gives the direction of the electric field due to the big charge configuration, and vice versa. Okay? Now, electric field of a point charge. Supposing the point charge is positive, then if I bring the test positive charge, I'm going to feel a repulsive force everywhere around the charge, pointing away from that source charge. So the direction of the electric field due to a positive point charge is radially outward. The direction of the electric field due to a point charge that is negative is radially inward, because if I bring my test positive charge to any point around the source, the negative charge, then the test positive charge will be attracted to the negative source charge. Hence, the direction of the electric field is radially inward around the negative source charge. And we can also draw the electric field line, which is continuous, and the electric field vector. The electric field vector allows you to know the direction of the electric field at a point, at any point along the electric field line. The illustrations are obvious. All right, how about other charge configurations? Next week I will show you how we can have a charge separation using conductors. and that leads to what we call a capacitor, in which we have positive charges on one surface and negative charges on the other. Between these separated charges, we have a uniform electric field, and the electric field lines are shown. So they are directed from the positive charge to the negative charge, and this is standard. How about 2-point charges, one positive, the other negative? If they are equal, as shown here, they constitute what is described as an electric dipole, and the direction of the electric field between those point charges is again from positive to negative. All right. Another point to note is that inside a metallic conductor, the electric field is 0. This is really good because inside your car, the electric field is 0 in general, and you will not be suffering from charge clings and things like that. If you get out of your car and it is cold and dry, you touch the door, you get a bit of a shock. But if you are inside, you don't feel, because your car is a sort of what we describe as a Faraday cage. Okay, so it provides a screening. So metallic conductors, inside them, the electric field is 0. We will demonstrate this further. Also, the charge arrangement is not always uniform. Where the conductor is pointed, then the density of charges is strongest. And that's the principle behind the way conductors used in preventing thunderstorms or electric discharges from destroying buildings. That's why those conductors are shaped that way. So you put them on a building such that if there is lightning discharge, then most of the charges will be concentrated on the pointed conductor, and this will enable the charges to be conducted away into the earth, thereby saving or protecting the building from destruction by the lightning. All right, now let's go into Gauss's law and electric flux. Gauss's law is so simple that it's hard to even, it's conceptually challenging to come to terms with it, but gradually we will do it. Basically, Gauss's law connects the electric field with a closed surface area. Okay? So if we have a charge inside a closed surface area, then we can think of the electric lines either going through the surface into the charge for the negative, or getting out of our surface from if it is a positive charge. So the density of the field lines and the area of the closed surface can be combined into one physical property described as electric flux. And Gauss's law simply says that the flux, the electric flux through a surface, is simply the charge enclosed, the total charge enclosed by the closed surface, divided by a constant which we call epsilon 0, and I will show you the constant. Here it is, epsilon 0. Physically, this constant is described as the permittivity of free space, and its value is 8.85 times 10 to the negative 12 coulomb squared per Newton meter squared. This will be given you on the formula sheet, so you don't bother. So here we have a cubical Gaussian surface. For instance, you will find a question on Flip It that is based on a cubical Gaussian surface. So if there is a positive charge or a negative charge inside, and we know the magnitude of the charge, we know the charge, then we can easily find the electric flux. The electric flux will be the total charge divided by this constant. For example, there is a Flip It problem that says, what is the electric flux through each side of a cubical Gaussian surface? That means you will just do 1/6 of the flux through the entire surface. Here is another Gaussian surface. This one is cylindrical. And even for this cat, we can make a Gaussian surface that doesn't have to be even uniform around it, and we find the flux through the whiskers of the cat. All right. So what then is the flux good for? It allows us to put together two quantities, the electric field and the perpendicular surface to the electric field. For example, here we have the perpendicular surface shown in brown, the brown square, and there is flux through it. But here, the surface, the brown surface here is not perpendicular to the direction of the electric field, so the flux is zero. Here, it is not exactly perpendicular. There is an angle between the perpendicular to the surface and the direction of the electric field. So the flux is then the perpendicular surface area times the electric field times the cosine of the angle between the perpendicular and the direction of the electric field. This is further illustrated here. So what again is electric flux through a surface? It has the Greek letter as its symbol, the big phi, and it is the product of the surface area and the electric field perpendicular to the surface area, the component of the electric field perpendicular to the surface. So it is AE cosine theta. All right. And Gauss's law says that this is simply the same as the total charge enclosed inside your Gaussian surface divided by this constant permittivity of free space. Gauss's law is great. We will talk a little bit more about it next week, but the basic thing we want you to know is that if you know the charge inside a Gaussian surface, then you know the flux, because this one is just a constant. All right? Now, there are nice flip-it problems to check whether you understand the simplicity of the definition of electric flux, namely that electric flux is just the charge enclosed divided by the constant epsilon 0 or epsilon naught, permittivity of free space. So supposing you enlarge the surface area from what it is, the darker region, to a bigger region, how does the flux change? Well, the flux does not change as long as the charge enclosed is the same. Interesting, yeah? The flux does not change because it is the same charge inside divided by a constant. All right, so mathematically it can be very involved. So it is an integral, a surface integral, but since we are doing this Physics 202 as an algebra based course, we are not going to go into the integral, but just know that there is more to it. So this is the question I was referring to, the flip-it question, where you are looking at a cubical Gaussian surface and you are given the charge enclosed, and you can find then the electric field because you know the surface area of your cube. So because of this symmetry in the geometry, then you can find the electric field due to the charge enclosed. Or you can pull out the A here, multiply it by E to get the flux, and then you are left with the flux being equal to charge enclosed divided by the constant epsilon naught. This is always true. Let's try a few problems. This one says, a positively charged solid conducting sphere is contained within a negatively charged conducting spherical shell as shown. So here is the positively charged solid conducting sphere. And that those pieces of information are important. It is conducting. It is spherical, meaning the charge is on the surface. The magnitude of the total charge on each sphere is the same. So plus Q is the same as minus Q. Only the sign is different. Okay? So inside them, the field is 0 because the electric field in a conductor is 0. Now the question, what is the direction of electric field between blue and red spheres? Yeah? Between the blue and the red spheres. Well, you have options. The field will point radially outward. The field will point radially inward. The field is 0. So make your choice. Well, it's going to be radially outward because while you are in this gap, you think of the area within which you are as a Gaussian surface. What is the charge enclosed? It is positive Q. Therefore, the field is going to be radially outward. Are there some field lines from negative Q coming in? Yes, but whatever comes in from the negative charge also goes out. Yeah. Whatever comes in from the negative also goes out. Therefore, the charge enclosed is just due to the positive charge, and the electric field is due only to the positive charge. The electric field of a positive charge is radially outward. Therefore, the electric field between the blue and the red spheres is pointing radially outward. Let's try another one. The same configuration, it says a positively charged solid conducting sphere, this one, is contained within a negatively charged conducting spherical shell, this one, as shown. The magnitude of the total charge on each sphere is the same as we had previously. Now the question, what is the direction of the field outside the red sphere? Outside this red sphere. Hey guys, let's use Gauss's law. Make a Gaussian surface outside the red sphere. And what is the flux? Well, the flux is just going to be the total charge enclosed divided by epsilon naught. But what is total charge enclosed? It's plus Q plus minus Q, which is 0. So there is no charge enclosed, and therefore the electric field outside is 0. Actually, many wires are formed this way so that the electric field around wires, conducting wires for circuitry in our homes and appliances, the electric field outside the wire is made to be 0 by this sort of arrangement. So this is important. Anyway, the answer is that the field is 0. Option C. And this is interesting too. It's the last one. A charged spherical insulator. So it is an insulator. It has inner radius A. Here is the inner radius, the white part. And outer radius B, coming from inside up to the blue part. The charge density on the shell is rho. Charge density here means charge divided by volume. So the question is, what is the magnitude of the electric field at dashed line? Some may be tempted to think it is 0 because it is a conductor. How about this? Let's use Gaussian law or Gauss's law to find the correct answer with the correct explanation. The charge is only in the blue region because the charge density is charge over volume. In the white region, there is no charge because the charge density there is 0. So the dashed line then has no charge inside it. There is no charge enclosed. The influence of the electric field coming from rho gets in and out. The field lines from any point will get in and out. So the total charge enclosed inside the dashed line is 0. and for that reason the electric field in there is 0. Alright, see you on Friday 2 p.m. for the help hour. Thanks for your attention. Take care. Bye.